Okay, so we're going to solve this problem right here by using the Bernoulli method. And we can see this is a standard Bernoulli method equation because we have the left side of the equation appears to be linear in standard form, and this side of the equation has a term that includes y to a power. And specifically, the power here is not 0 or 1. If it was 0, then this would be just a standard linear equation because there would be no y here at all. And if this power was something other, if it was 1, then I could combine it with this term. But since it's not either of those things, it can be any real number, then this is the form that I need in order to solve for Bernoulli. So what we're going to do is we're going to first simplify the equation to try to get rid of this y to the power in one of these terms. And then we're going to make a substitution in order to solve the problem the rest of the way. So the first thing that we're going to do is we're going to multiply by an expression of this form. And the reason that we want to do that is first we're going to essentially divide by y to the power. So here n is 3. And this term right here is just a constant, but it's going to come in handy later on when we make our substitution. And so you can leave this 1 minus n term out, but it will make it easier later on. And so rather than do an extra algebra step later on in the process, we're going to just incorporate it here. So in this case, again, n is 3, so 1 minus 3 gives me minus 2, and y to the negative n is going to give me y to the negative 3. And so I'm going to take this term and I'm going to multiply it all the way through my equation. So my original equation was y prime, and then I'm going to multiply y prime by negative 2y to the negative 3. And then my original term here was negative 5y, and here's my negative, and here's my 5y, and I'm multiplying it by my multiplication factor, negative 2y to the negative 3. And then same thing over here. This was my term on the right side of the equation, and I'm also multiplying it by negative 2y to the negative 3. Now, as we simplify, nothing can really be simplified for this first term, so that stays. For the second term here, my signs cancel. 2 times 5 is 10, and then y to the negative 3 times y to the 1 reduces when I add the exponents to y to the negative 2. And on this side, negative 5 and negative 2 gives me 10. The x stays the same, and then the y to the 3 and the y to the negative 3 cancel, which is what we were trying to achieve in the first place. Now, the substitution that we're going to make in order to turn this into a linear equation is going to depend on this term right here that used to be the linear term. So if we follow down the math, this is where the linear term used to be. And this is our substitution variable. So we're going to replace y to the negative 2 with another variable. I'm going to call it z. And then I'm going to take the derivative of this because in solving a linear ODE, I have to have z and z prime. So I take z prime, which is the derivative with respect to x, and using the power rule, negative 2 comes down, I subtract 1 from the exponent, and then I multiply by the chain rule, y prime. Well, that turns out to be exactly this term. Now, it's exactly this term because I put the 1 minus n up here. If you don't put the 1 minus n up there, you will get a term that has all the same y components, the power of y and the y prime, but it will not have the right constant on it. So, as I said, you can still make the substitution, but you will need an extra step of algebra if you don't have the 1 minus n. Okay, so we make our substitutions. Negative 2y minus to y to the negative 3, y prime. That just gets replaced with z prime. And then the z goes in for y to the negative 2, so I just get 10z. And then nothing happens on the right side of the equation. And so this is now my linear term, my linear equation. All right, so solving this by the method of integrating factors, just like you would a regular linear equation, the thing in front of the linear non-derivative term, it goes into the mu function, e to the integral of 10x, or 10 dx, and I get e to the 10x. And then I multiply my whole equation through, and this turns into a product rule. So e to the 10x, if I take the derivative of it, I get 10 e to the 10x. And then z, if I take the derivative of that, I get z prime. So I can simplify this into fg, so e to the 10x, z, quantity primed. And then on this side of the equation, nothing happens. And now I can integrate both sides with respect to x. On the left side of the equation, the prime and the integral are just going to cancel to give me this, e to the 10xz. But on this side of the equation, I'm going to have to do a product rule because I have an x and I have an e to the 10x. So I'm going to split this up. U is going to be x, and dv is going to be 10 e to the 10x to make my integration a little easier. And then du will just be the derivative of u, which is dx, or du, and du equals dx. And then the antiderivative of dv is going to be e to the 10x. So the left side of the equation, again, remains the same. My u, which is the x, and my v, which is the e to the 10x, minus du and x and v. So I'm just going to get e to the 10x dx. And then integrating that is going to give me negative 1/10 e to the 10x. And then my constant of integration. Now at this point I need to solve for z. And so if I solve for z, I'm going to multiply everything by e to the negative 10x, or I can divide by e to the 10x, whichever way I prefer to think of it. And so the e to the 10x here is going to cancel on the x. Here it's going to cancel on the negative 1/10, but leave the negative 1/10 in its place. And then the constant also has to be divided by e to the 10x. And so I'm going to write this as e to the negative 10x so that I can multiply instead of having a fraction. Now we're not quite done yet. In order to completely finish, I need to get y back into the equation. So recall from way up here, z is equal to y to the negative 2. And so my equation now is going to become y to the negative 2 is equal to this whole expression. Now, this is an implicit way to express the function. I could, if I preferred, maybe it would look a little less standard, a little more standard, a little less wonky if I did this. But if I wanted to solve the equation for y, I would end up having to take the reciprocal of both sides of the equation. Which isn't going to be pretty. And then if I take the initial conditions, if there are any available, into account, then I can come up with an explicit expression for y is either plus or minus the square root of 1 over this crazy thing. And again, whether you use the plus or the minus will depend on your initial conditions. If y turns out to be negative, you would use the negative square root. If y starts out to being positive, then you'd use the positive square root. And you could use that initial condition, of course, to solve for the constant. But if you're going to solve for the constant, I recommend doing it up here, someplace where the sign is less important.